A desperate idea, an abandoned bomb experiment, and 2 flashes of light. How physicists finally detected the neutrino, 26 years after Pauli first proposed it. By Physics Explained. Trillions of ghost particles are passing through your body, and you don't even notice. They're called neutrinos. Last month marked the 70th anniversary since neutrinos were first detected. Neutrinos are weird particles, and I am going to write a lot of articles about them. But in this article, I am going to focus on the history of how they were detected, because it is very interesting. If you're reading this, you're already my kind of audience. I write here on Substack, post companion videos on YouTube, and also share episodes through my podcast. Subscribing is the easiest way to support the work. And if you're able to pledge, it makes a real difference. The problem with beta decay. The story starts in the late 1920s with a problem with a reaction called beta decay. An atomic nucleus is made of protons and neutrons, and sometimes that mix is unstable. Every nucleus requires the right amount of mixture of neutrons and protons. When an atom has more neutrons than needed, it tries to fix the imbalance with beta decay. In the most common form, beta minus decay, one neutron inside the nucleus transforms into a proton, and in the process it ejects an electron. That ejected electron is the beta particle. The trouble is that this looks like a two-body decay, a neutron turning into just 2 particles. Two-body decays are rigid. Conservation of energy and momentum leaves no freedom, so the outgoing particle's energy is fixed. Every electron should come out carrying the same amount of energy. But when scientists actually measured the energy of the electrons coming out of beta decay, they found it wasn't fixed at all. Some electrons came out with high energy, some with very low energy. What they got was a whole distribution, a spread. And that was not what they were expecting. There were 2 things that could be going wrong. Either energy conservation doesn't hold at the subatomic level. Maybe it wasn't a 2-body decay at all, and a 3rd particle was coming out with the electron, carrying off the missing energy. Both answers had serious backers. Niels Bohr, one of the greatest physicists, was willing to drop energy conservation. He thought it might hold only on average across many decays, rather than in every single one. He'd tried the same move before in the 1920s for the interaction of light and matter. Another physicist, Pauli, made another proposal. Pauli made his proposal on December 4th, 1930, in a letter to a physics meeting in Tübingen that he wasn't attending. It opens, "Dear radioactive ladies and gentlemen." He sent it by courier, with a colleague who could explain the idea in person. He called it a desperate remedy himself. His suggestion was that nuclei contain electrically neutral particles with spin 1/2, light enough to be somewhere near the electron in mass, and certainly no heavier than 1/100th of a proton. He called this particle a neutron. Enjoying this? I cover space and physics in plain language over on YouTube too. Subscribe here, YouTube. Then in 1932 Chadwick found the real neutron. It was heavy and neutral, and it solved the nuclear structure problem on its own, but it was far too massive to be what was slipping out of beta decay. Pauli's version needed a different name, and Fermi gave it one, neutrino, the little neutral one. So how does it fix the spectrum? If a neutrino comes out alongside the electron, and the 2 energies always add up to the same total, the paradox dissolves. The sum stays fixed. The split doesn't. Sometimes the electron takes most of it, sometimes the neutrino does, and what you measure across many decays is a spread. The rest of the letter is him hedging. He isn't sure what forces act on the thing. He guesses it might have a magnetic moment, and reasons that it can't ionize matter any more than a gamma ray does, which is his first stab at how weakly it interacts. He says outright that he doesn't feel confident enough to publish. He admits the odds are against him, since a particle like that probably would have turned up by now. He mentions that his predecessor Debye told him not to think about it at all, the way you don't think about new taxes. His answer to that is that only people who bet can win. Then he apologizes for not coming to Tübingen, because he's needed at a ball in Zurich the same night. Fermi took Pauli's idea seriously and built a theory around it. There was a stretch where physicists thought the particle couldn't be detected at all. Beta and Peales put it in print in 1934. There was no practically possible way of observing the neutrino. They had calculated the odds of a neutrino hitting anything, and the answer was that it could pass through 1,000 light-years of solid matter before interacting once. The verdict held about 12 years. Then Bruno Pontecorvo, one of Fermi's students from Rome, wrote a report saying it was too strong. By 1946, he was in Canada at Chalk River, standing next to a reactor, exactly the kind of neutrino source that hadn't existed when Bethe and Peales ran their numbers. He didn't argue with the physics. He agreed the yield was tiny. What he disputed was the conclusion. The literature said the process couldn't be observed, and Pontecorvo called that too drastic. Observation was not out of the question with modern experimental facilities, and he had a method in mind. The method used chlorine. A neutrino hits a chlorine-37 nucleus and turns it into argon-37, which is radioactive with a half-life of about 35 days. That's the clever part. You don't have to catch the interaction as it happens. Let a big tank of chlorine-bearing liquid sit for weeks while argon builds up inside it. Then flush it out, concentrate it, and count the decays at your leisure. You're not detecting a neutrino anymore. You're detecting a few atoms of gas in a tank, and chemists were already good at that. He named the two sources worth aiming it at: the sun and nuclear reactors. Nobody built it. The report was classified, so it sat unread for years. Meanwhile, in the United States, two physicists at Los Alamos were going after the neutrino with a completely different plan. The bomb, and then the reactor. Frederick Reynes and Clyde Cowan started from the same basic reasoning. If a single neutrino is nearly impossible to catch, flood the area with an unimaginable number of them and wait for the rare one to interact. Their first idea, in 1951, was to put a detector next to an atomic bomb test. A fission explosion releases a huge burst of neutrinos at once, and they sketched out a detector, nicknamed El Monstro, to be dropped down a shaft near a 20-kiloton test tower and take 2 seconds of data before the blast arrived. Getting a bomb assigned to a physics experiment turned out not to be the hard part. The plan was approved. It was never built. In late 1952, they were urged to reconsider by J. M. B. Kellogg, head of the Los Alamos Physics Division, who suggested a nuclear reactor instead. Reactors were still in the early stages of commercial development, so this was not the obvious suggestion it now sounds like. Reynes wrote later that he had wondered since why it took them so long to reach what seemed such an obvious conclusion, and how it escaped everyone around them they'd talked to. Pontecorvo had written it down 6 years earlier, in a document they had no way to read. Their first working detector, at the Hanford Reactor Site in Washington State in 1953, was a real piece of engineering. 300 liters of cadmium-doped liquid scintillator watched by banks of photomultiplier tubes, wired to catch a specific double signal. They nicknamed it her AUG, Mr. I. They saw a small effect that seemed to depend on whether the reactor was running, and published it under the title Detection of the Free Neutrino, with the careful phrasing that it appeared probable the aim had been accomplished, further work in progress. Nobody was convinced, including them. Cosmic rays had swamped the detector with false signals roughly 10 times larger than what they were chasing. If you're reading this, you're already my kind of audience. I write here on Substack, post companion videos on YouTube, and also share episodes through my podcast. Subscribing is the easiest way to support the work. And if you're able to pledge, it makes a real difference. Learning what was fighting them. They treated the failure as a list of things to fix. Better shielding, better electronics, a stronger reactor, a longer run, and above all, a proper understanding of what was faking their signal. That last one turned into detective work. Cowan later described testing materials one by one to see which were quietly radioactive. Brass and aluminium were worse than iron and steel. Even the potassium in the glass in their own light detectors was giving off a faint signal of its own. Everything going into the experiment had to be checked first. The new site was the Savannah River plant in South Carolina, which had a far more powerful reactor. The detector they built there in 1956 was much bigger. Large tanks of the flashing liquid, wrapped around thin tanks of water dosed with cadmium. The water was the target, the part the neutrinos would actually hit. They buried the whole thing 12 meters under. Round, behind 11 meters of concrete, and packed lead and wax around it to keep everything else out. The trick was in the signature. The reaction they were watching for was an antineutrino hitting a proton in the water and knocking out two things: a positron, which is the electron's antimatter twin, and a neutron. Those two leave very different trails. The positron dies almost instantly, meeting an ordinary electron and annihilating in a burst of light. The neutron lasts longer. It drifts through the water for a few millionths of a second until a cadmium atom swallows it, and that produces a second burst of light in the same spot. So the signature was a flash, then a pause, then another flash in the same place. Nothing else in the detector does that. Stray radiation might produce one flash, but getting two in the right order, right distance apart in time, and the same location is almost impossible by accident. That pattern is what let them pull a real signal out of the noise. The telegram. They ran for months, comparing the count rate with the reactor on against the reactor off to make sure they weren't fooling themselves. Roughly 2.55 counts per minute with the reactor running, versus 2.14 with it shut down. On June 14, 1956, they sent a telegram to Pauli in Zurich, telling him they had detected the particle he'd proposed 26 years earlier. Their results were published in Science on July 20th, and a fuller paper titled simply, "The Neutrino," followed in Nature on September 1st, reporting a reactor-dependent signal of 2.88 plus, or minus 0.22 counts per hour. The measured cross-section came out around 6 times 10 square centimeters, which is roughly what Bethe and Peales had calculated in 1934. They'd had the physics right the whole time. Pauli was reportedly delighted. The thing he'd worried might never be found had turned up after all. Raynes received the Nobel Prize in 1995. Cowan had died in 1974, and the prize doesn't go to the dead. The timeline is worth seeing together. 1930, Pauli proposes the particle. 1932, Chadwick discovers the neutron. 1934, Fermi develops the theory of beta decay, and Bethe and Peales calculate the tiny interaction probability. 1946, Pontecorvo proposes using reactors and radiochemical detection. 1951, Raynes and Cowan consider using an atomic bomb. 1953, the Hanford experiment sees an uncertain signal. 1956, the Savannah River experiment detects the neutrino convincingly. 26 years from the idea to the detection. That is not unusual in particle physics. The work runs on patience, and many people give a whole career to a question and come away with nothing. If you want to understand what's actually happening in spaceflight, explained in plain language, without the press release gloss, consider subscribing, and if you can, a pledge helps me dedicate more time to writing and keep the blog going. If you're reading this, you're already my kind of audience. I write here on Substack and post companion videos on YouTube, and also share episodes through my podcast. Subscribing is the easiest way to support the work. And if you're able to pledge, it makes a real difference.